Get started, and welcome everyone to today's session on sustainable design using precast concrete. We're delighted you could join us today. You'll get one HSW credit for attending today's session, and we ask you to stick around till the end to make sure you achieve that full credit. We also have the opportunity for you to ask questions, so use the Q&A function in your Zoom bar to get those questions queued up, and we'll get to them at the end of the session. We've built in some time for that, so we appreciate the interaction from the audience as well on anything that you see in the presentation. Today, we're privileged to have one of our partners in the industry talk about this topic with us. Jim Snyder is here. Hi, Jim.
Hi, Mike. Hey, everybody.
Jim's the Executive Director of PCI Mountain States, which is a chapter of the Precast Prestressed Concrete Institute. That includes Colorado, Idaho, Montana, Utah, and Wyoming. With a background in publishing and communications, Schneider has worked in the design and construction industry for over 15 years. He's a lead AP and former editor of EcoStructure magazine, who has written numerous articles, including in numerous publications, including Architect and Retrofit. Schneider currently serves on numerous PCI committees and councils and is involved in the precast industry's sustainability and resiliency efforts. So we are, again, pleased to have Jim here and hear his expertise on this very relevant topic, as we're all striving to be more sustainable in our environment and better stewards of the climate, and have a variety of tools in the toolbox to do that. So we're hearing about how precast prestressed concrete is one of those tools today. Without further ado, we'll turn it over to Jim, and I look forward to seeing you later for the questions. Thanks, Jim.
Thank you, Mike, and thanks everybody for joining us today. It's a topic that's pretty near and dear to my heart, so I'm looking forward to chatting a little bit with you guys about it. As you know, anyone who's dealt at all with sustainability knows it's a broad topic and there's lots of different considerations and approaches. So kind of what we're going to be talking about today is, at least from a material perspective, ways that precast prestressed concrete can be part of that sustainability conversation, or sort of part of the mindset in ways of creating sustainable and resilient buildings. So with that, I'm going to mute my little face here so that we can get into the Oops, hit the wrong mute button. There we go, that's better. So anyway, today's presentation is called Designing for Sustainability Using Precast Prestressed Concrete. As Mike mentioned, this is good for one HSW credit, registered with AIA. As you mentioned, am with PCI Mountain States, and this is just a quick list of our members. Here in Colorado, you may have met with or dealt with NCON, StressCon, Wells Concrete, or Plum Creek Structures. So as we mentioned, credit stuff, so we'll get this registered for you. You should have a certificate within a couple of weeks. Quick course description. This course will discuss considerations for the holistic design and construction of sustainable structures that perform efficiently and offer occupants and communities safe, healthy, and useful spaces that could be effectively utilized over many years. We'll examine LCA data and discuss ways precast prestressed concrete can contribute to sustainable, durable, efficient, and resilient buildings. So today's learning objectives will define sustainability and life cycle thinking and examine how these concepts impact the long-term performance of a building and the health of its occupants. We'll discuss a little bit about LEED version 4, actually 4.1 now, EPDs and LCA, and examine how holistic design can impact the health, safety, and welfare of occupants and the community. We'll learn ways that precast can contribute to energy efficiency and indoor environmental quality, and understand the relationship between durability, resilience, and sustainability. So what is sustainable design? Of course, it's, as we mentioned earlier, it's kind of something that's got a lot of different approaches and thought processes behind it, but this is from the U.S. General Services Administration definition of the topic. Sustainable design seeks to reduce negative impacts on the environment and the health and comfort of building occupants, thereby improving building performance. The basic objectives of sustainability are to reduce consumption of non-renewable resources, minimize waste, and create healthy, productive environments. Now, these are a lot of different things, of course, that we try to accomplish with a sustainable building. And, you know, sometimes it can be, you know, some of these goals can sort of compete against each other. You might get into, you know, discussions of, you know, material impact versus long-term performance of a building versus, you know, indoor environmental quality, and a lot of these different things. So I think really the challenge in any project is to find the right balance of those things to achieve the most sustainable building possible. And of course, the reason we're doing it is, you know, climate change is an issue, and buildings are a part of that. Of According to the United Nations Environment Program, buildings and their construction worldwide account for 36% of global energy use and 39% of energy-related carbon dioxide emissions each year. U.S. Energy Administration data from 2018 shows that residential and commercial buildings account for 40% of the energy usage in the U.S. According to U.S. Green Building Council, buildings account for 13.6% of potable water use in the U.S., the third largest category behind thermoelectric power and irrigation. Building industry consumes about 40% of raw materials from the global economy each year. And also, EPA estimates that 569 million tons of construction and demolition waste were generated in the United States in 2017. It's more than twice the amount generated by municipal solid waste. So certainly the building industry has an impact, and any way we can find to help mitigate that and minimize it is certainly going to be a positive. Buildings account for about 28% of global emissions each year and about 11% of embodied carbon emissions. This is from Architecture 2030. So different approaches to sustainable design. This comes from the whole building design guide. The main objectives of sustainable design are to reduce or completely avoid depletion of critical resources like energy, water, land, and raw materials, prevent environmental degradation caused by facilities and infrastructure throughout their life cycle, and create built environments that are livable, comfortable, safe, and productive. Different ways to get about that. So optimize site potential, really make the most of the site that you're building on so that you're disturbing as little of the environment as possible. Optimize energy use, again, the energy efficiency part of it, so that we're utilizing less energy over the long-term life of a building. Protect and conserve water. Optimize building space and material use. So this is again about really, we can't avoid using building materials and building buildings, but what we can do is think about how do we create buildings that are, stand the test of time, that don't need to be torn apart and rebuilt every few years. So how do we optimize that? Enhance indoor environmental quality, because, of course, one of the main goals of a building is to provide a healthy and safe environment for people to be inside. So we want to make sure that it's something healthy and positive for occupants. And also to optimize operational and maintenance practices. So, of course, there's impact going into the building of a building, but how is that also spread out over time? How much maintenance and upkeep is required? And build for resiliency and adaptability. Again, if you're thinking about the long life cycle of a building, and this is part of what we'll be talking about with precast concrete specifically, we can build buildings that stand up for quite a long time, but can you anticipate how that building is going to be used in a few years, and can it then be adapted? And also, will it be resilient to things like storms and climate change and other types of challenges that the building may face over time? We'll get into some of that as we go out throughout the presentation. So really, I look at this as taking a holistic approach to sustainable design. Like I mentioned earlier, trying to find that right balance. This is again from U.S. General Services Administration. Utilizing a sustainable design philosophy encourages decisions at each phase of the design process that will reduce negative impacts on the environment and the health of occupants without compromising the bottom line. It's an integrated, holistic approach that encourages compromises and trade-offs. Such an integrated approach positively impacts all phases of a building's life cycle, including design, construction, operation, and decommissioning. So benefits of sustainable design. Of course, environmental benefits of just reducing the impacts of the natural resource consumption, whether that's through, material choice or how you're going about the construction of a building. Economic benefits, you can improve the bottom line. I'm one who does firmly believe in the idea that sustainability can also be an economic benefit, whether that's through long-term performance of energy efficiency, just the overall positive health of a building. That's a good thing. Health and safety benefits, once again, protecting the occupants, providing them a healthy space and a safe space. And community benefits, minimizing strain on local infrastructures, improving quality of life. So, building is part of a larger piece in its community, and does it serve its function over a long period of time with minimal impact on the community and its environment. So strategies for sustainable design using precast. As part of a holistically designed, sustainable structure, precast, pre-stressed concrete can contribute in several areas, including durability and resiliency, which I've just touched on a little bit. We'll go into that in a bit. Energy efficiency. It's also, there are attributes of precast that can be helpful to the overall energy efficiency strategy of a building. Life cycle performance, we'll get a little bit into some LCA data later. Indoor environmental quality, again, part of that health and safety for occupants. And material efficiency, because it is precast pre-stressed concrete is something that's made under plant conditions and controlled, in a controlled factory. It's, basically, it's very resource efficient. It's very site efficient because it comes to the site already made, the components, so it's a lot less disturbance, but we'll get into some of that stuff a little bit later in the presentation as well. So high performance, durability, and resiliency. Precast concrete is a high performance material that integrates easily with other systems, inherently provides versatility, efficiency, and resiliency to meet the multi-hazard requirements and long-term demands of high performance structures. If you're familiar with the Energy Independence and Security Act of 2007, it defines a high performance structure as one that integrates and optimizes on a life cycle basis all major high performance attributes, including energy and water conservation, environment, safety, security, durability, accessibility, cost benefit, productivity, sustainability, functionality, and operational considerations. And when we're thinking about precast, it can have an impact in all of these areas and do that, make that positive impact over a long life cycle. It could be 100 years plus with a building built to precast. And, that's kind of the important thing to consider there. I won't go into all of this, but basically just a few thoughts about attributes and benefits of precast, essentially in three main buckets that we talk about. It's versatility, efficiency, and resiliency. The versatility piece of it can look like a whole lot of things. You can do thin brick, you can make it, a lot of aesthetic flexibility, also structural versatility, because precast can be load bearing and architectural at the same time. In terms of efficiency, we'll be getting to some of this stuff in this presentation. Site efficiency, the minimal site disturbance I just mentioned, energy efficiency, and then resiliency. That's an important part of the equation. I think where precast relates to sustainability is the fact that it can, weather severe events, stand up to it, live a long, productive life as a building, which then minimizes its impact over a long period of time. So on that note, durability. Precast pre-stressed concrete is a strong, durable, flexible material that can deliver a 100-year service. Because a precast building can function deconstruction, and construction are energy and material intensive processes. So the longer the building stands up, the more impact is mitigated. And this is an interesting example. This picture right here is the Baha'i Temple in Illinois, which has been around since it was actually started construction in the 1920s and was finished in the early 1950s. And it's beautiful, ornate precast that's been around for a long time in a somewhat harsh environment and has stood up really well. And continues to perform at a high level. So resiliency is the ability of structures and communities to effectively adapt to changing conditions and maintain functionality in the face of stress, environmental change, or extreme events. Resilient communities are those with structures, systems, and infrastructure that are sufficiently durable and flexible to continue operation during or immediately following an extreme event or change. So we see here a couple of examples of the kind of devastation that can happen with severe weather events, which is something that we see all across the United States, particularly in certain parts of the Midwest and other parts of the country. But, as climate change starts to change the overall weather dynamic, we're starting to see more of these in different parts of the country and parts of the world. So it's something that we do have to think about. Resilient structures provide the strength and durability to perform their functions in a changing environment, endure and suffer minimal damage from storms, fires, floods, earthquakes, and blasts, and quickly return to a functional state afterward. That's the key component of resiliency, is not only does the building stand up to a challenge like a storm or a fire, but can it then return to usable function and serve its community and its purpose going forward. A building's first challenge or first responsibility really is to protect its occupants and stand up to that event, but then can it be used with minimal repair and get right back to work afterwards. Resilient buildings protect and serve their occupants and their community, even in the face of adverse conditions. A resilient building contributes positively to a community function over a long lifespan. So just a quick example here. If you might remember the tornado that hit Joplin, Missouri back in 2011, it was an extremely destructive F5 tornado on the ground for 20 minutes. It destroyed pretty much the entire town. 162 lives were lost, and Joplin High School was one of the buildings that was destroyed in that storm. And kind of an interesting story from that community where Precast is concerned is that there was a freestanding Shopco big box store that was in town that actually stood up to the storm. And it was decided within the community within a few days that that would become first the temporary place for the Joplin High School to continue. And then it wound up actually being retrofitted into Joplin High School. So it was an example of how Precast was able to stand up to a severe storm event and also exhibit the kind of flexibility that allowed it to be transformed into a completely different use and serve its community within a relatively short period of time. So advantages to resilient design and construction. Resilient buildings deliver long and effective service life, provide safety and well-being to occupants, effectively resist hurricane and tornado force wind, earthquakes, fire, or blast incidents, minimize disruption and reduce recovery time for individuals and communities, provide sufficient functional resilience to ensure nearly continuous operation even in the face of environmental change and severe events, provide benefits for insurance and overall long-term investment, meet the needs of communities seeking structures and buildings that perform above code and add to their overall resiliency equation. So how this really relates to sustainability is the fact that if a building can endure these kinds of events and continue to serve its purpose over a long period of time, that means you are not deconstructing and reconstructing a building in its place, which is an extremely material and energy intensive process. So, Precast is durable, resilient, and safe, has a long service life. Again, the good indoor environmental quality, functionally resilient from multi-hazards like storms, earthquakes, and blasts, and able to suffer little damage or quickly return to service after an event. So here's a couple of little visual examples to show you. This is a wind cannon test that was performed on some different types of wall systems by basically taking a 2x4 and shooting it at 100 miles an hour through a couple different walls. We'll see the impact here through a vinyl and wood frame wall. It obviously goes right through. Next up is a brick on wood frame, which also the wood goes right through that at 100 miles an hour also. Brick and steel frame slows it down, but still does make it through. And then finally, we have a precast concrete sandwich wall panel, which resists the impact entirely. So this is why, particularly in parts of the country where you see a lot of storm hazard, we see safe rooms for communities built out of precast, or parts of schools, things like that, to make sure that its occupants remain safe. So that just gives you a visual example of that. And a different type of event that we also have to, think about maybe a little bit more out in this part of the, country, or Utah, which is part of my territory, is seismic. And this is a shake test that was done, I believe, in California, replicating a 9-point earthquake using a moment resisting precast frame, or a self-righting moment resisting frame. And you can see how the connections allow it to actually move and go back into shape. So again, you can design for seismic with precast in different ways. That's one example. But it's another thing that, another event that we have to think about standing up to when we're thinking about resiliency. And finally, on some government projects, we have requirements for blast as well. And there was a blast test done with precast a number of years back. And you'll see a few different angles in this video. And as we'll see, there's a couple of interior shots coming up where you'll actually see the panels move. The pre-stressing strand allows them to be just flexible enough to absorb that blast energy and then actually go back to position. So protecting the occupants, but then also not failing and allowing the building to continue to stand and go back to doing its business. So those are some of the things that we talk about with resiliency. So that's a big component when we're thinking about precast in terms of sustainability, is essentially that it performs really well over a long period of time, even when you throw very difficult challenges against it. But another thing to consider is energy efficiency, because, as really when we look at the impact of buildings on the climate, big part of the energy or embodied energy that goes into buildings, or its big impact, is in its operation over time. And we have a little bit of data on that later as well. But so we really want to create the most energy efficient buildings possible, because that, first of all, saves energy, and second of all, that does affect positively the bottom line of a building's operation over time in terms of just economics. You're spending less money on energy. So envelope performance is affected most by heat loss and gain for opaque assemblies, heat loss and gain through fenestration, curtain walls, etc., air leakage, moisture. So how do we manage heat? We control heat flow by using insulation, which is essentially a blocker to heat flow. We also eliminate short circuits, which is thermal bridging. If you have steel stud wall, for example, and the thermal energy can go through those studs, it can short circuit the what you're getting out of the insulation. So that's something we have to think about and have that continuous insulation barrier. Also eliminate air and moisture leaks. And a bonus is the utilized thermal mass, which is something that you can get by using concrete, the thermal mass effect, which we'll touch on a little bit in a moment. So ASHRAE 90.1 requires continuous insulation. Continuous insulation is insulation that is continuous, as it would imply, across all structural members without thermal bridges other than fasteners and service openings. This can be located, the insulation can be located external, internal, or integral to any opaque surface of the envelope. So the thermal bridging, this is kind of showing an example through thermal imaging. You can see where those short circuits happen in the top photo with the steel stud wall, whereas with the precast sandwich wall panel below, none of the heat is escaping through that assembly, just going out through the doors and windows in that case. So actual performance is based on the entire wall assembly. So really you have to take into account more than just the material R value of, oh, my insulation is at this R value and the wall material is this. You have to actually also factor in what you're going to lose in terms of that short circuit through thermal bridging, or what you might gain in terms of thermal mass. So that gives you the actual performing R value. So hence an R19 2x6 stud and cavity wall, it doesn't actually perform at an R19 because of those thermal bridges, those short circuits. It'll actually perform closer to an R9, and it actually does make you account for this. So because steel conducts heat much more efficiently than other materials, that's why we see that kind of issue. So ASHRAE 90.1 requires a correction in the values used in a steel stud cavity wall, just like we just discussed. So for a 6-inch thick steel stud 24 OC wall with R19 bad insulation, the corrected R performance is R8.6. And this actual performance or effective R value should be used in determining the heating and cooling loads for HVAC. So thermal mass actually gives you an impact in the other direction. So if you're not familiar with the thermal mass effect, it basically, concrete sort of works as a thermal battery. It absorbs the heat inside or through the wall system slowly, so it sort of releases slowly throughout the day and off of peak hours. It creates a more consistent temperature, and also allows you to, oftentimes downsize your HVAC. So the chart on the right shows a 24-hour thermal cycle for 3 wall systems, 2 stud and cavity walls, and a precast concrete sandwich wall system. It's important to note that all 3 wall systems have the same U factor or thermal transmittance, which means the only difference between them is the thermal mass. Thermal mass of precast concrete creates a lag which shifts peak heating and cooling points relative to when they occur. Notice the traditional walls occur shortly afterwards, whereas the precast wall occurs several hours later. Some areas of the country, these peaks occur when energy rates are less expensive. Maybe more important is the reduction in the magnitude of these peaks. That means we're using less energy to heat and cool the structure due to the thermal mass effect. So, thermal mass also does help you create a more uniform temperature, reduces large fluctuation, and increases occupant comfort. It's important to note that thermal mass will vary based on where your project is located. Environments where the outside temperature fluctuates above and below the set point will have the greatest benefit. So where it's cool in the morning, hot in the afternoon, it affects the way that heat moves through the wall. And, this is an important thing that you can take into account and have calculated for you if you're looking at using a precast wall system it can make a positive impact on what your HVAC load is going to need to look like. So ASHRAE 90.1 acknowledges the benefit of thermal mass. And so in this example, in a region like Chicago, where the maximum wall U factor for mass concrete walls is 0.90. For steel frame walls, the maximum U factor is 0.064. But you can see here with a continuous insulation on a mass wall, you get a higher level of performance. This is an example of what a material R value might look like if you just total up the, what the actual materials are. So interior air film 0.68, 7.5 inches of concrete on the inside is 0.60. 2 inches of XPS insulation is 10. That's a continuous insulation. 2.5 inches of concrete 0.2. Exterior air film 0.17. So you get the material R value of 11.65. But as this example shows, you might have a material R value in this example of R11.33. It actually performs at R26.1. So that's a pretty compelling example. Like if you factor in the thermal mass effect, this is a project in California. Material R value of the sandwich wall is calculated at 11.33, but due to the thermal mass of the wall system and the fact that there's no thermal bridging, the effective R value is much higher at R26.1. And again, how we achieve minimizing those thermal bridges is that we use non-conductive ties, like a carbon fiber type of material, to tie the wall system together, so you don't have metal moving that thermal energy through. So it's something to talk about with your mechanical engineer or your engineer. And there are firms that will calculate this stuff for you, but it's certainly something to consider when you're looking at the overall thermal performance of your building. It can help you downsize your HVAC equipment, tonnage reduction in this case of up to 37%. So that can be, those are just some of the ways that you can think about precast in terms of energy efficiency, particularly when you're thinking about sandwich wall panels with continuous insulation. You get that thermal mass effect you can also factor in. It can make a real difference in the long-term energy impact of your building. So life cycle performance. So environmental impact. What's the environmental impact of using precast concrete relative to other systems? So, the question is, of course, you're always considering all kinds of different trade-offs and considerations when you're looking at a building. How does precast factor into this when compared to other materials? So PCI conducted a comparative cradle to grave LCA life cycle assessment a few years ago. This means to look at all factors, this goes from everything from harvesting the raw materials, production, transportation, and even disposal. So cradle to grave. The LCA was conducted by a third party consisting of Morrison Hirschfeld, the Athena Institute, and Venta Glazer and Associates, and was conducted in accordance with ISO 14040 and 14044. So third party verified. The baseline building was a 5-story office building designed for 130 person occupancy. Building was designed in accordance with IBC 2006 and ASHRAE 2007. 73-year service life was assumed, window wall ratio of 0.4. Building was modeled in 4 climate zones: Miami, Memphis, Denver, and Phoenix. The structural systems were evaluated along with 5 enclosure systems. So 3 structural systems: steel, cast in place, and precast, and 5 enclosure systems: curtain wall, brick and steel stud, precast, insulated precast with thin brick. So this made for 15 different combinations through this study. So the findings, first of all, and this is important across, no matter what your decisions are, and this is seen in, if you look at any data about building impact on the environment, the operating stage, the use stage, is really where you get the biggest environmental impact for any building, any structure enclosure combination. So about 96% of the building's impact is over its use stage, not the construction part of it. The covariance among structure enclosure combinations for a given climate zone was 2% or less. So basically, the findings from the study show that in almost all categories, the differences are within the margin of error of the analysis. So in other words, there's no significant difference in environmental impact between the systems over the service life of a building. That means essentially material and system selection can be based on the benefits of the material and systems. What it basically boils down to is precast does not impose additional environmental burden relative to the system studied. So when you consider Of course, we'll talk a little bit about embodied carbon and some of that stuff as we come up, but we know that concrete does create CO2 emissions in its manufacture. But when you consider the fact that it lasts such a long time and gives you such a benefit over that period of time, it spreads that impact out over many years because it has a longer service life than some other comparable materials. So it becomes essentially a push in that respect. And then you can also think about some of the other benefits that you're getting by using precast, as we discussed. So what is embodied carbon? It's certainly a term that's out there quite a bit right now. Architect magazine did an entire issue of it earlier this year, so it's certainly something that's on a lot of folks' minds when we're thinking about sustainability. And then some of the definitions out there of embodied carbon do vary. Some view the embodied carbon of a building as including the entire life cycle of the materials, including the operational phase of the building. Full life cycle view of embodied carbon would account for the impacts also of landfilling and recycling, so deconstruction and what you do with the material afterwards instead, or as well, I should say. Others focus just on the initial embodied carbon, which is the impacts associated with extracting, manufacturing, and transporting materials to the job site. So something closer to cradle to gate. Carbon is something that we use generically to talk about greenhouse gas emissions, not just carbon dioxide. But I will note that according to ISO standards, embodied carbon does indeed focus on the entire full life cycle, not just cradle to gate. So any greenhouse gases also emitted during maintenance, repair, rehab, end of life go into that equation as well. A couple quick definitions of embodied carbon from the UK Building Council, or Green Building Council. In the building life cycle, embodied carbon is the carbon dioxide equivalent or greenhouse gas emissions associated with non-operational phase of the project. Circular Ecology says embodied carbon is a carbon footprint of a material. It considers how many greenhouse gases are released throughout the supply chain and is often measured from cradle to gate or cradle to site. So all building materials contribute to the carbon footprint of a building in different ways. So, it isn't as if, you can really say like, oh, one building material has like, very little embodied carbon impact, whereas others have, there are variances. It just kind of depends on how you look at it. So a lot of it's all about consideration. So concrete, does contribute 6 to 11% of global CO2 emissions. Much of it comes from the production of Portland cement, which comprises about 10% of the concrete mix. Producing aggregate also does require some energy, but that's mostly from transportation. That's a minimal part of the equation. And this, by the way, is all from that Architect magazine issue from earlier this year. Steel, manufacturing virgin steel from iron ore is extremely energy intensive. The global steel sector also has a large carbon footprint, contributing upwards of 10% of global CO2 emissions. Wood, its manufacturer produces fewer emissions than steel and concrete, but there is still some debate over its overall impact because there isn't a whole lot of research yet on the carbon emissions of the logging, processing, transport, and maintenance of wood products. So there's kind of more to that equation as well. Material mitigation. Of course, all the different industries talk about ways that we can work through this and better, serve the environment and reduce impacts over time. In terms of concrete, there's a few ways at that. One is by using supplementary cementitious materials, which is not only fun to say, but it also does reduce the cement content. So you use things like fly ash to help reduce emissions. Another thing is when we're talking about that aggregate impact from later, aggregate transportation impact can be mitigated by local sourcing. So that's something to talk to your precaster about if you're looking at precast concrete, is trying to use local aggregate. And also with, with concrete in general, manufacturing impact is spread out over a very long life, as we discussed earlier. With steel, they'll talk about using recycled steel versus manufacturing virgin steel, which does produce or does require less energy. The wood industry talks about the carbon sequestration in its material. However, it should be noted that that carbon is released at the end of the material life or as the material burns or decomposes. Just a couple of quick notes from a study that I saw, an international study called Emissions, talking about kind of the idea of long-term embodied carbon with like wood versus concrete specifically. What it basically gets into is that if you look at, yes, just the baseline CO2 that's created by making concrete versus wood products, that makes, concrete does have a bigger impact in and of itself. But when you also factor in things like the regeneration rate of the trees, soil carbon loss, and conversion of natural forest, combine all those factors and it makes it a lot more even. It's much like the LCA study that we talked about before. When you kind of look at the big picture of all of it, it does kind of come to the same place. And the same, if we look at it with a more life cycle use, by factoring in the use part of the equation with wood versus concrete, because concrete stands up longer, requires less maintenance, some of that stuff, like it tends to even out if you look at it over time. So, it's worthy of note, of course, removing trees, even though you're planting new ones, that does, there's still some, we're still trying to understand a little bit the difference between what, how much CO2 a fully mature tree removes from the environment versus one that's newly planted. And certainly foresting practices have come a long way since the advent of FSC and things like that in the last 20 years, but we're still trying to get an understanding of some of that data as well. So carbon costs, essentially what it boils down to is all building materials have a carbon cost. The challenge for designers, owners, is to consider the benefits, attributes, and costs and specify a material mix that best suits a project's environmental goals. So it may be, it's just kind of looking at what you're trying to achieve in terms of your sustainability and just overall performance goals for your building, and figure out what material mix is going to work best for you. Where precast concrete can be a positive is that it does have an upfront carbon impact, but mitigates that impact over a long life cycle and by performing at a high level over that life cycle. So that's kind of how to think about precast. Another place that precast can make a positive impact in the overall sustainable operation of a building is in the area of indoor environmental quality. So concrete is a low emitting material. It's an inert material. So using precast walls reduces off-gassing, often attributed to other materials. Many finishes don't require painting or coatings, which again can have off-gassing or chemical makeup. Because precast is inert, it does not require VOC-based preservatives like wood products do. And textured interior walls can provide aesthetic alternatives to VOC-emitting paints or wallboards. So in the case of like a precast concrete sandwich wall panel, which is what we're looking at here, you can actually finish the interior concrete with paint, and you don't really need to do anything else with it. You don't have to fur it out. You don't have to use drywall. So there are some advantages to that as well. Utilizing thermal mass means that buildings need less energy to heat and cool, and that goes, not just into the energy performance of a building, but also, gets into just the occupant comfort. Thermal mass does create a more even temperature, and creates a high level of occupant comfort as well. Also durable and inherently fire resistant. Concrete buildings provide security for occupants. So concrete is not flammable. It does hold up well against fire and other types of challenges that go into that resiliency conversation we had a little bit earlier. So precast floors and walls provide also a high sound attenuation. And I think this is something I've been hearing a lot more in the conversation where it comes to indoor environmental quality is what's the sound quality like? And, one of the things that's great about precast is that it does have very high sound attenuations, STC ratings north of 55. So if you use, hollow core planks for walls, for your floors and ceilings, you don't hear the people walking around on top of you. You don't hear the people in the rooms next to you if you have or traffic outside or anything like that if you have precast wall panels. So it's another positive for indoor environmental quality. Also, long spans allow for open areas well suited for daylighting. And that, by the way, also plays into the thing we touched on a little bit earlier about the adaptability of buildings. Precast, you don't have to have so many columns all over the place, so you have a lot of flexibility in terms of what you can do for interior design. And material efficiency. So job site efficiency and health, scheduling efficient on-time deliveries of precast minimizes vehicular idling time and traffic congestion. So, it's basically when you're using precast, you're dealing with materials that are built in a plant, shipped to the job site, ready to assemble. And, it can be a very well planned, pretty seamless operation, and with minimal crew and minimal resources on site. And you can really save time and energy that way. It's also really good for tight urban environments. Reduced airborne dust and debris because all that work isn't being done on site. The pieces are finished when they arrive. Use of modular systems minimizes construction waste. That's another thing to talk about with precast, material efficiency. I mean, if you're going to be using concrete, it is a very efficient type of concrete. You're using less material, and it's under, being made under very controlled conditions. And also, education of field personnel. We have qualified plants, qualified erectors to ensure high quality control. Plant efficiency. Reusable forms reduce waste and debris at the job site. We do reuse forms over and over again as often as possible, so we don't have to constantly be making new forms and using new materials. Construction sites are also cleaner and neater because, again, this work is done under controlled conditions at the plant. Steel forms are used to cast structural precast products. These forms have a long lifespan, providing thousands of reuses. And specialty shaped molds are stored for future use. So, once again, this is kind of one of those areas that gets into the, where we're thinking about both efficiency of resources and, economy. Like it's costs, we're saving money by not, constantly rebuilding new things. It's good for the bottom line of a project and also good for the environment at the same time. Recycling and reuse. Precast can be crushed and recycled for things like road base. So that is something that it can be done at the end of its life. But what's also interesting is precast elements can be engineered so they can be disassembled and reused on a project expansion or a different project altogether. And a really interesting example of that is the Olympic Stadium that was done in Atlanta a bunch of years back there. It was later to become Turner Field, but when it was built with the idea that several riser sections would actually be deconstructed and removed. And I believe it was 4 riser sections came out and were used for local high schools in the area. So that was kind of a neat example of how precast can be reused in different ways. And now last, we're going to talk a little bit about precast as it relates to LEED. I don't know how many of you folks are doing LEED projects these days, but of course, if you're not familiar, LEED is the Leadership in Energy and Environmental Design, U.S. Green Building Council. It's a program that's been around since 1993. Definitely has made a big impact on the construction and design industry, and has changed quite a bit over the years, and the new version is a little bit different than previous ones. So the new version of LEED, or newer version of LEED, does emphasize highly the life cycle analysis concept. So it's a lot of kind of what we're talking about, I think earlier versions of LEED were a little bit more focused on, what a particular materials, quote, sustainability was, or how much recycled material was in something, or, different parts and pieces like that. The newer versions of LEED are trying to look more holistically at a building's long-term life performance, the long-term impact of the products that are in it. So it emphasizes product transparency, life cycle analysis, and environmental product declarations. So the assessment of a product's environmental impacts covers all stages of life, including material sourcing, transportation, energy, manufacturing, usage, and recycling or disposal. So types of life cycle assessment, and some of these terms have come up already in the presentation, but cradle to gate is basically what it takes to manufacture the product and have it get to the gate of the factory. So what it takes to the materials that are taken in it, what it's taken to actually manufacture it. So that doesn't factor in transportation to the site, its use over time and all those kinds of things. Cradle to grave. Cradle to grave is, taking a little bit a bigger look at the product, both from, all the way from its point of creation to its disposal. So that also includes transportation to the site, construction, its use, maintenance over time, deconstruction, and disposal at the end. So that's a bigger piece of it. And cradle to cradle is a concept that you may have run into, but this is basically the idea of sort of there being no waste. Of a material being used, or manufactured, used, then deconstructed and recycled and reused as something else. So that's just a different, more holistic look at life cycle assessment. So the idea of product transparency is what we're getting into with environmental product declarations. So LEED version 4 and 4.1 encourage a degree of product transparency that requires industry to manufacture and develop, industries and manufacturers to develop product category rules, PCR, product life cycle assessment, LCA, environmental product declarations, EPDs, and we're also, at some extent, you might see out there health product declarations, HPDs. So all of these things are basically getting to the bottom of what the impact of a product or system is, and then trying to be as transparent as possible about it. So really the deliverable in terms of LEED and really any of this is getting down to the HPD and EPD, mostly EPD, environmental product declaration, which is essentially like a nutrition label for a product. So you're getting a lot of, kind of just the basic breakdown of what's in it so that when making specifying choices, designers and owners can be confident in the fact that the manufacturer has been transparent with what's in a particular product. So the way it works and breaks down, and this is quite a process, by the way, for manufacturers to come up with an EPD. It's not just something that, you quick throw together. It's a process that takes a few years typically, and first requires the development of a product category rule, which is something typically that an industry will develop, and it defines the scope of the LCA. So it basically defines what a product is. So you kind of come up with an overarching set of statements that are what a particular product, what incorporates a concrete wall panel or whatever it is. And then the life cycle assessment analyzes the data specified in the PCR, measures all the inputs, outputs, and environmental impacts across the product lifespan from cradle to grave. So that's the real data heavy part. The life cycle assessment gets into all the nitty gritty of the impacts of manufacturing, sourcing, transportation, all that stuff over time. And what that produces is just an immense amount of data. I sort of compare it a little bit to the Human Genome Project, where that went on for years, and it came up with just an incredible string of data, which is amazing. But what then do you do with that? How is that translated into anything that's usable? And that's where the environmental product declaration comes in. So the EPD summarizes data collected by the LCA as specified by the PCR, enabling comparison of environmental impacts across product categories. So what this does then is create that transparency, that label that says, here's the environmental product declaration for what I'm producing. And those can be product specific, they can be industry specific, and LEED does award those in different ways, which we'll get into in a second. Independent and third-party verification, very important part of this process, because as you probably recall, at the early version, early days of the green building industry, early versions of LEED, there was a lot of greenwashing and folks just saying hey, this thing is sustainable, isn't that great? So it's something beyond just a company saying, hey, my product is sustainable. It's actually requires third-party verification so that the designer and specifier can know, all right, this transparency has actually been verified by somebody. Just a quick note on health product declarations. Again, these come up. It doesn't really, you probably won't see it too much in relation to precast, but it tends to be an interior finish thing. But what it basically gets into is, making sure there's no very low chemical composition in the different types of products that you have, so that you don't have that that off-gassing, the impact on indoor environmental quality. So that's where a lot of the health product declaration comes in. It's not as common as an EPD, and a lot of industries don't really have this yet or much with it. But if you run into the term, that's what it is. So just a couple of quick notes about precast and LEED 4.1. 110 possible points in 7 main credit categories. So there's a different point breakdown here, to get different levels from certified, silver, gold, platinum. So a couple of areas where precast can make a difference with LEED is so location and transportation. This category is designed to contribute to communities that reduce overall vehicle transportation. So what this gets into, or precast can arguably make a difference, is that it's really good for multi-story tight site construction, in dense urban environments, which is kind of what this encourages, walkable communities, things like that. And because the components are manufactured in a plant and shipped to the site, precast is ideal for tight urban sites, like where you don't have a whole lot of room to maneuver. Precast can be a really positive material to use for that. So it can help you, and also does create minimal waste and site disturbance. Sustainable sites. The main intent of this category is conserve natural areas, restore damaged areas, and promote biodiversity. Areas precast can help here is, precast can allow you to incorporate parking into the building footprint, which limits site disturbance. You can also use vegetated roofs. which contribute to this credit. Site shading, reflective precast hardscapes to reduce the urban heat island effect. You know, it's something you can talk to, you know, your precaster about, using lighter aggregates or like white cement and things like that for higher albedo, so you can have more reflectivity in your building. So this is some of the considerations you can have here. Cool little green roof example here of actually like a soccer field that's actually a green roof on a parking structure at the bottom right there. Energy and atmosphere. This one seeks to reduce overall energy usage by encouraging building to aim for higher levels of energy efficiency. And this is where using thermal mass and those insulated wall panels can really make a difference. So, you know, definitely think about that thermal mass quality and in your approach to this one. Materials and resources. Previous versions of LEED approached materials by encouraging the use of recycled and rapidly renewable materials. LEED version 4 focuses on that life cycle approach that we've talked about. So this gets into the EPDs, the LCAs, and all that stuff. Precast is extremely durable, long-lasting material whose lifespan and flexibility spread its environmental impact over many years. And just a couple quick notes getting into what it means to get the credit on this disclosure and optimization approach with EPDs. So disclosure is basically the minimal requirement. They require a certain amount of environmental product declarations from a certain amount of manufacturers. Disclosure is basically meeting the minimum, and optimization is by having product impacts that are below industry average, environmentally preferred products, and that eliminate hazardous chemicals. So once again, those environmental product declarations, comprehensive, commonly formatted report, which documents how a product affects the environment throughout its life cycle, third-party verified, you know, so the EPD comes after having the life cycle assessment and the product category rule determined. And I believe what LEED requires at least 20 products sourced from 5 different manufacturers with EPDs, and there's a different impact. Like, so there's product specific life cycle assessment. So that's just the LCA. You get 0.25 of a product of that 20 if it's, excuse me, just the LCA. If it's an industry-wide EPD, which in the case of, like, for example, precast concrete, we do have an industry-wide EPD that goes across, you know, PCI members, and that gives you 0.5, so half of a product. And if you have a product-specific EPD where a manufacturer has specifically gone out and gotten a life cycle assessment and an environmental product declaration of its specific product done, that gives you a full product. So that's kind of how that spread works. That's something you have to consider when you're going into a product, so, or project. So you get, you know, 1 credit for the disclosure by meeting those requirements, and you get another credit for hitting the optimization, like the really high performing products in that. So just a note on that. Indoor environmental quality, as we discussed earlier, this is intended to encourage healthy spaces, free of contaminants, and provide adequate light, sound attenuation, and fresh air. Because precast is an inert material that doesn't emit VOCs, the flexibility of precast allows large open spaces that contribute to daylighting design. Precast has a very high STC level, providing excellent sound attenuation. Regional priority credits. This is something that's, I think, new to version 4.1. But basically what this is different regional chapters of the U.S. Green Building Council come up with things that are specific to that area. So these target credits will give additional points for criteria in those areas that are, you know, of concern in that area. So here in Colorado and the mountain states in general, most of the regional credits are related to water conservation. Precast can contribute in the areas of energy efficiency and urban density, which I think are some of the regional credits also here. So that's kind of just a quick summary of LEED. And you know, again, I know it's out there. People are still pursuing it. I don't know if it's to quite the extent that, you know, the cachet that LEED had a few years ago, but you know, it is still a factor in the industry. It's made a lot of changes to the way we look at buildings, so I think it's definitely had an impact over time. But other green building programs that exist that are out there that you may encounter: International Green Construction Code, Green Building Initiative is Green Globes. That was one that kind of started, I think, around the same time as LEED and was sort of an early competitor. Living Building Challenge, which is indeed a challenge. That's a tough one to achieve, but quite a comprehensive program. Collaboration for High Performance Schools, and also the National Association of Home Builders has a green building program, among others, I'm sure. So there's lots of different avenues out there. because as we've discussed, there's a whole lot of different ways to think about sustainability in buildings. So in summary, precast concrete is a long-lasting, durable, and efficient material that inherently provides the versatility and resiliency needed to meet the multi-hazard requirements and long-term demands of high-performance structures. The flexibility and longevity of precast buildings mean they can be used and reused for decades, providing excellent performance for generations and spreading material impact over a long life cycle. And that is pretty much what I have. I want to really thank everybody for joining me today.
All right. Thank you, Jim. I want to come back up here so we can see your smiley face. So appreciate that presentation. A lot of content. I want to invite people if they have any questions about something they saw before we wrap up here. If they want to ask that Q&A feature, we've got a little bit more time left to handle that. And if there's something you'd like to contact Jim directly, he's got his contact information on the screen as well.
Yep, there we go. Oops. Yes, definitely. Yeah, it's a couple of quick notes there. I can be contacted at jschneider@pcims.org, or pcims.org is our website. So yeah, feel free to reach out with questions or comments or anything. Definitely.
Yeah, and even though you've got a large region, he's right here in Westminster. So
I am. That's correct. I'm right here in the neighborhood.
So obviously you've done this presentation multiple times. Tell us a little bit about how it was developed and who you've been giving it to.
Well, this is actually kind of pulled together from, there's parts of it that are from research that PCI has put together over time. Certainly they've done their LCA study, and some of it having to do with high performance is something that we've been talking about for a lot of years, and the energy efficiency component of things. So there's a lot of studies that have been done on thermal mass and that effect on buildings. So I've been able to take from PCI. One of the things about the organization that's been around for like 60 years, are the national chapter, they've got just an incredible amount of data about the performance of the buildings and the material over time, and something that they've done an excellent job of compiling. So there's a lot of great resources there that I've pulled from to help assemble this together. And also just a little bit from my own background coming in, I did work in in the sustainability realm for a while. I was at Hanley Wood, which produces Architect magazine. I worked there for a number of years on EcoStructure magazine and some other publications, and it's got some background in that area as a lead AP and everything. So it's something that I think, for me, sustainability, because there's so many different ways to, so many different considerations and ways to get to a different building goal, depending on what it is you're building and where you're building it. I'm always kind of fascinated by what a particular system or product can contribute, and what the trade-offs are and how you go about it. So that's kind of how I went into this presentation.
And if someone were to specify some precast material, it wouldn't come from very far away potentially, right? There's
correct.
Colorado.
Yep. And that's exactly it. And that's one of the things about precast, is that it is, it's heavy, like it's a big, and so it tends to be a local and regional material. Like you do generally go to, we have, several precasters here, that do work, within a space like they do, we've had some local precasters here do work in Montana, for example, but primarily, when you're dealing with precast, it is generally a local specification. And one of the things too, is in this part of the country, we've got a lot of great aggregate at our fingertips too, like that we can get to. That's pretty, so the sourcing doesn't have to come from very far either. So there's that advantage as well.
Great. Well,
yeah.
I want to thank you again for a remarkable presentation. It's definitely something that's on a lot of people's minds. So we appreciate hearing what's happening in the field. And like you said, there's no one size fits all solution. Everything
Correct.
The building type and the program and other goals of the client will weigh in on this, but it's nice to know what you get with a particular kind of product and how it's aiming to address those sustainability goals that we all share. So appreciate you sharing that, Jim, and want to let people know Again, you will get 1 HSW credit for attending today. And in the future, we have some more virtual connects coming up. Tomorrow, we have a session on AIA Colorado's legislative successes. In the session that just recently concluded, it's the top 8 impacts of legislation on Colorado practitioners from this spring. And then next Tuesday, we have a panel discussion featuring previous recipients of the Architect and Young Architect of the Year awards from AIA Colorado. And they'll be talking about how they are adapting and pivoting right now and what the awards have meant to them in their careers since receiving it. So we hope to see you soon, either tomorrow or next week or sometime down the road. And again, thank you for joining us. And thanks, Jim, and to your company for being part of our efforts.
Thank you. Thank you, AIA Colorado, and thanks everybody for being here. Appreciate it. Thanks for your time today.